I'm building a massive 100 square foot blindingly bright video wall in my basement. If you need to ask why, well, you probably don't know me very well. But a more practical reason is that my wife won't let me build it anywhere else. I'm doing this on a budget, so I can't afford those $100,000 plus professional video walls. And I don't want one of those El Cheapo LED curtain wall $200 Amazon specials. So I'm going to have to get creative. Use off-the-shelf LED strips and some custom LED controller hardware and software I've been developing for the last year. This project is probably going to cost more than I expected, take longer than I'd hoped, and will probably have 2 or 3 major redesigns, which means it'll go perfectly. But if you want to see how I drive thousands and tens of thousands of LEDs without melting down my circuit breakers or my marriage, stick around because things are about to get very bright. Oh boy, that's bright. Hi, I'm Josh, and this is Signal Drift. I've been using the very high I/O bandwidth of the Raspberry Pi Pico to shovel LED pixels at very high frame rates. Last year, I built this animated Christmas tree with about 1,000 pixels, and it was able to hit over 120 frames per second. I hand-built a controller box with a Pi Pico and a 250-watt power supply and level shifters on a custom solder board. It was a real pain in the butt. But this project pushed me to design a custom PCB that incorporated all of my learnings. I've been iterating on this design, and the final version is almost done. Each board can drive 10K plus LEDs at liquid smooth frame rates, delivering 50 amps of power at 12 volts. And I can daisy chain them together with Cat5 cables. One of the primary reasons I wanted to design this video wall is I wanted to take this custom video controller design to its very limits. Not with thousands of pixels, but tens of thousands of pixels, requiring multiple controller boards. Here's the wall. Where I live, basements tend to be shallow. The ceiling here is only about 7 feet tall, but the wall is long, about 16 feet or roughly 5 meters. Now I'm planning to have the video wall take up most of this wall. I'm targeting about 2 meters tall or 6.5 feet and 4¼ meters long or about 14 feet. That's about 10 square meters or 100 square feet of surface area. It's a beautiful blank canvas, and I want to fill it with an ocean of LEDs. This project sits squarely between those El Cheapo video curtains that you can find on Amazon for $200. What's that, like 3 frames a second and a couple hundred pixels? And the professional video walls that cost hundreds of thousands of dollars. They are insanely bright with very high frame rates, low pixel pitch, high resolution, low response times. They're good enough to game on. My wall's price, resolution, and pixel density will sit squarely in the middle of these two. These are 30 LED per meter LED strips. That's about 3.3 centimeters spacing between each pixel, or about 1.3 inches. My video wall at 2 meters tall, this will give me about 60 pixels of vertical resolution. The horizontal resolution depends on how tightly I pack the strips side to side. With an almost perfectly square layout, with horizontal spacing being the same as vertical spacing, on a 2 meter by 4.3 meter wall, I'm looking at 172 by 60 resolution for a total of over 8,800 pixels. That's over 1,000 pixels per square meter or 100 pixels per square foot. That's roughly 8 times the El Cheapo video curtain. Doesn't seem like much, and 172 by 60 resolution isn't even CGA level resolution. So let's call that option A. What about option B? Well, these LEDs come in different linear densities. This is 30 per meter. They come in 60 per meter and 144 per meter. 144 is a little out of the league that I want to attempt, but I can definitely look at 60 per meter. That's double the linear density, and when we put that in a 2D array, we get quadruple the total number of pixels. Running the numbers, I get a video wall with 273 by 120 resolution with over 32K LEDs. That's about 25 times the $200 El Cheapo video wall. But this scales heat, power, and complexity to a whole other level. Here's a visual comparison of how the two options would look. This is a visual simulation that I wrote to show the relative pixel density at the same aspect ratio of the actual video wall. Now, this video isn't one where I've already built the entire wall and I'm going to show it to you in the end. This is purely the prototype stage. I want to walk you through the design, and I'll need your help to help make a couple of key decisions. Well, let's talk about the construction and materials in this video wall. Option A or option B are purely about the LEDs and the support electronics. The physical construction of the wall, however, will remain identical. I've broken up the design into 7 removable modular panels that hang on the wall with French cleats. The design has a simple backer board that I attach the LEDs to, and then we mount a diffuser at a fixed offset above the LEDs to spread the light and hide the physical strips and electronics. Breaking the design into modular panels makes install, test, and maintenance much easier. And it lets me validate the design, cost, current draw, and heat by building just a fraction of the total video wall. With such a large display by surface area, the cost of the mounting hardware could easily spiral out of control. I need a cheap, stable, flat substrate that helps to spread heat. If I had an unlimited budget, I'd buy a stack of aluminum sheet and call it a day. But that's prohibitively expensive. So I decided on a composite approach. I do need a heat sink, but it needs to be cheap. Aluminum flashing is cheap, but it's very flexible. I could mount it to plywood, but plywood is still relatively expensive and very heavy. So I found this wonderful cheap material called tempered pressboard. It's basically cardboard with some sort of plastic or resin impregnation. A 4x8 sheet, 1/8 of an inch thick, costs about $15. And I can get 2 of these panels out of 1 sheet. So the total cost is only about $7.5 per sheet. But unfortunately, the pressboard by itself is relatively brittle and it's not a very good heat sink. So what if I bonded this aluminum flashing to it with contact cement? Does that sound crazy? Well, let's find out. The plan here is to build a throwaway prototype and build just one of the total 7 panels. By committing to not using what I'm going to build, I can freely make mistakes and try things out. The point here is to learn. I cut the press board to 24 inches by 2 meters. Yes, you got that right. 24 inches wide and 2 meters long. The reason for this is that the LEDs come in meter sizing and the aluminum flashing comes in 8-inch widths. I live in hell. So I cut 3 8-inch wide, 2 meter long strips for each one of the panels. I rolled contact cement onto both surfaces and let it tack up while I had dinner. But that was a little too long. With contact cement, drying too long can reduce the bond strength. Even so, they mostly stuck together, but in my final build, this is something to adjust. So on to the LEDs. I started with 1 strip just to test adhesion and layout and the electronics, and here we go, we got it to light. Then I laid down 300 LEDs to get some realistic numbers on current draw and power consumption and heat. I could have dimmed or split the power supplies, but I had all the data that I needed. 600 LEDs provided me more than enough data, and interestingly enough, heat just wasn't an issue with this panel. But because I was able to get all the data I needed from 600 LEDs, I stopped short there. I didn't build the entire panel. Remember, this is just going to be a throwaway, so I've used it for additional testing, and I'll use it as a reference, but there was really no point in populating the rest of this thing with LEDs. It would have just been a waste of LED strings. So let's go through the numbers on power and heat. I measured with a bench power supply and 600 LEDs at 12 volts and full white, pulled over 6.5 amps, at about 78 watts. For option A, that's a manageable 1200 watts. Totally doable on a single North American 15 amp 120 volt circuit. And for heating, it's like a very small room heater, but spread out over a huge surface area. With the amount of ventilation this will have, I don't imagine heat is going to be much of a problem. Power management, however, is still an issue. 120 watts at 12 volts is still 100 DC amps. Now, I probably don't want to run 100 amps of power through a hobbyist PCB. So I'll probably need at least 2 boards, if not more boards, and this particular issue from my testing forced me to revisit my PCB design and bulk up some of the power planes. When we take these numbers and apply it to option B, we get an insane 355 amps at 4,300 watts. Now, this is not doable on a single North American household electrical circuit. Matter of fact, it would probably require 3 or 4 circuits to power the wall at 100% brightness. And there's no way I'm running 355 amps through even multiple different versions of my hobbyist controller board. And at these levels of power dissipation, for option B, heat could become a really serious issue. So for option B, I'm going to need some dimming, probably about 25 to 30% of the maximum power, and multiple circuits or potentially both. It's important to remember that real-world usage won't be full white all the time, but we've really got to plan this design around the peak power utilization. So what did I learn from the prototype build? What are my takeaways? I validated the power and heat requirements, and I think I've got a good plan for both. With a redesign, my custom PCB can handle the power just. I've validated the construction of the backer board here. The pressboard sandwich is flat, light enough, and cheap, and spreads heat well enough for this particular application. The LED strips come with a nice 3M adhesive strip, and once this cures, it really sets up well. It adheres well, so I don't have any issues with bonding. But I did find that applying the LED strips consistently is very hard. Alignment in both directions is difficult. So for my final production build, I'm going to need some sort of an alignment jig or registration harness to make things line up better than they did on this. It's not awful, and if I got this level of accuracy for the full video wall, you probably wouldn't notice, but I'll notice. Now, the camera here doesn't really do this justice, but even with this small prototype, the brightness is insane. The full video wall is going to be incredibly bright. And finally, I feel like I've gotten comfortable working with this particular brand of LED strip. I've never worked with them before, but after a few false steps, I came up with a good soldering and wiring approach that I think will work in scale to hundreds of LED strings. And scaling that is going to be key. Remember, option B, for example, has over 100 5-meter LED strips. That's a half a kilometer. Each panel will have 39 2-meter strips with soldering required on both ends and sometimes in the middle. Times 7 panels, that's over 2,000 individual solder joints. If I'm not a soldering expert now, I will be at the end of this project. So I've got to make a decision. Option A or option B. I was just talking about soldering complexity, for example. Option A will have about half the amount of soldering as option B. It's also cooler and has a lot simpler power distribution and signaling complexity. But it also feels just a little bit too easy and basic. It doesn't even have 10K pixels. So I'm torn. Well, what about cost? Let's talk about the relative cost of these two panels. And really the key difference here is in the LEDs themselves. The diffuser turned out to be relatively expensive. I'm using hobbyist grade frosted plexiglass for the diffuser, and these are not cheap. They come in 2x4 panels, and I'll need 2 of them for each one of these panels. So I'll need 14 of them total. At $61 each, that's almost $900 for the diffuser alone. The backer board is super cheap. Remember, I can get 2 of these panels out of each sheet of backer board, and they only cost $14 to $15 each. So the total cost for that is $57. The flashing comes in 8-inch by 50-foot long rolls, and I've run the calculations and I'll only need about 3 of them to finish my 7 panels. So that comes out to about $100 for the flashing. The big expense in both options, however, is the LEDs. For the 30 per meter pixel strings, which is what I have right here, they cost $15 each, and I'll need roughly 70 of them with some margin for the option A design. Remember, that's the 147 by 60 resolution with 8.8K total LEDs. So at a unit cost of $15 for 70 of them, that's a total cost of about $1,000 for the LEDs alone, leaving us with a grand total cost for option A of $2,600. For option B, the only cost that changes is the LEDs. The LED strings themselves are slightly more expensive, and I'm going to be using a lot more of them. So I estimate that with some margin, I'll need about 120 of them, and at $22 each, we get about $2,700 for the LEDs alone. This ends up with a grand total cost of about $4,300 for option B. So in the end, when you talk about cost comparison, option B is only about 40% more expensive than option A, but comes with 4 times the resolution. It's really tempting. So tempting, but also so intimidating. So what do you think? Do I go with the still massive but pixel sparse 8.8K LED array? Or do I go all in with a 32K LED wall, which will be a lot more work and probably require some truly heroic power and signal distribution work? Let me know your pick in the comments. Once I make the decision, in the next installment, I'm going to show you the completed controller board, and I'll also show the full build and operation of the final version of one of these panels. We'll look at the panel wiring harness, the power injection plan, and even look at the software that allows us to treat alternating linear strips like a 2D addressable plane of pixels. Thanks again for watching. I'm Josh. This is my basement, and we're just getting started.